Hi everybody, in this video I'll be talking about drag force. In a couple of previous videos we talked about drag force of an object moving through the air, and so in this video we'll look at objects moving through a fluid. And the equation for drag force is the force in pounds is equal to a drag coefficient times the specific weight of the fluid times the frontal area of the object times its velocity squared divided by 2g. So let's look at a submarine moving through the ocean, and it's going 10 knots, which is equal to 17 feet per second. So the specific weight of the seawater is 65 pounds per foot cubed, and the kinematic viscosity is 16 times 10 to the negative fifth feet squared per second. Now this coincidentally is the same as air at standard conditions, so I don't think there's any meaning behind that. It's just a coincidence, but it does give us an easy comparison of the force from wind drag, or drag force from air, and drag force from water, because it would just be a ratio of the specific weights, all other things being equal. So that ratio would be 65 divided by 0.075, which is about 860. So the force from the seawater would be 860 times that of air. Okay, so let's say our submarine is 30 feet in diameter, and so that would make the frontal area 707 feet squared. Okay, now we need to calculate the Reynolds number to look up the drag coefficient. So that would be diameter times velocity over the kinematic viscosity. So 30 times 17 over 16 to the negative fifth equals 3.2 million. Okay, and then we'll look at a log scale, and a useful trick for that is to just take the log of 3.2, and that equals 0.5. So we'll look halfway across that category of Reynolds numbers. So here's our drag coefficient chart, and we'll assume that the submarine is a circular cylinder with this 5:1 ratio. So we'll just follow this line over to 3.2 million. That's going to be between 1 million and 10 million, and halfway over. So we are right here, and that would mean our drag coefficient is about 0.38. Okay, so now we can calculate the drag force. 0.38 times 65 times 707 for the area times 17 squared divided by 2g, which is 64.4, and that force is equal to 78,400 pounds. And then the horsepower to overcome that drag force would be foot-pounds per second divided by 550. So 78,400 divided by 550, and that equals 2,420 horsepower. And then if we assume the propellers on the submarine are 60% efficient, then our brake horsepower would be this 2,420 divided by 0.6, which is 4,040 horsepower. And that would be the power required from the engines. Okay. Now let's look at another example of a steel ball falling through SAE 40 oil, and it's a steel ball with a 1-inch diameter. So we'll find its terminal velocity, which will be equal to its weight. In a previous video, we looked at a 1-inch steel ball and we calculated the weight as 0.148 pounds. So that will be the drag force. The area, the frontal area, is 0.0055 feet squared. The viscosity of this oil is 200 centipoise at 100 degrees Fahrenheit, and its specific gravity is 0.9, so that means its specific weight will be 0.9 times 62.3, which is 56 pounds per foot cubed. And then I'll need density for this, so 56 divided by 32.2 is 1.74 slugs per foot cubed. Okay, now centipoise is a metric measurement of viscosity, and so we need to convert that to English units. And what I use is 1 centipoise equals 1 over 47,880 pound-seconds per foot squared. So 200 centipoise is going to be 200 over that, which is equal to 4.18 times 10 to the negative 3, and that is dynamic viscosity. But to calculate Reynolds number, I like to use the kinematic viscosity, so we'll convert to that. And kinematic viscosity is the dynamic viscosity over the density, so that would be the 4.18 to the negative 3 over 1.74, and that equals 0.0024 feet squared per second. Okay, so I'm going to jump over here to the drag force. We know the force is going to be 0.148 pounds. So 0.148 equals our drag coefficient times specific weight times the area times v squared. We'll solve for that, divided by 64.4. Oops, 64.4. Okay, now there's two unknowns there, so I'm just going to make an assumption on the drag coefficient, and I'm going to assume that it is 1,000. So that would be right here, and then we go up to the line for spheres, and we see that the drag coefficient will be 0.55. So I'm going to put that in there, and then we solve for velocity. So V equals 7.5 feet per second. Okay, now we'll calculate the Reynolds number to see if it was close to our assumption of 1,000. So the Reynolds number equals diameter times velocity. So we have 1 over 12 feet times 7.5 over the kinematic viscosity, 0.0024, and that equals 260. Okay, so we're off a little bit. We need to make an adjustment. So the log of 260 is, or log of 2.6 is 0.41. So the 260 would be between 100 and 1,000, and 0.41 over, 41% of the way over. So about right here. And we'll say that that drag coefficient is 0.75. Okay, so we just recalculate that. 0.148 equals 0.75 times 56 times 0.0055 times the velocity squared over 64.4. And so our new velocity is 6.4. Okay, and then we'll recalculate the Reynolds number to see if it's close to 260. So 1 over 12 times velocity over the kinematic viscosity, and that equals 222. Okay, and the log of 2.22 is 0.35. So we go to the same area, make a small adjustment. It's about 1/3 of the way over. And I'm going to say it's right there at 0.8. So going through that same process with 0.8 here and solving for velocity, we get a velocity of 6.2 feet per second. And so I'm going to stop with iterations right there and say that's good. So this steel ball falling or sinking through SAE 40 oil goes 6.2 feet per second. Okay, thank you for watching.